Hello everyone, welcome to the world of magnesium and its alloys. My name is Dikai Guan and I'm a new tutor for this magnesium alloys module. We will go through the basics of magnesium alloys and their applications in the following weeks. I hope we will have a nice journey. The objective of this lecture are shown in the following topics. First, we need to know a bit history of magnesium. For example, when the scientists first discovered it. Second, how and when the magnesium alloys are used. Do we need around magnesium alloys products? Third, we need to have a clear picture of the main physical properties of magnesium alloys. Otherwise, we're not 100% sure why the magnesium alloys are used in situations. As you might already know, magnesium is very active in atmosphere, especially when it is humid. So we will cover the process of magnesium extraction from natural minerals. Last but not least, the main deformation systems, including snip and painting in magnesium alloys, will be discussed. I believe Martin already provided you a list of recommendation books regarding aluminum and titanium alloys. We also need to read some reference books which will help you understand magnesium alloys. For example, Magnesium Technology, Metallurgy Design Data Applications written by Friedrich and Modak. Magnesium was discovered in magnesium oxide by Joseph Black in 1755. The name magnesium originates from the Greek word for locations related to the tribe of the Magnetes, a district in society called Magnesia. The pure but tiny amount of the metal itself was first isolated by Humphrey Davy in 1808 using the electrolysis of magnesium oxide in England. However, it was the French scientist Antoine Boussy who made a sizable amount of the metal in 1831 by reacting magnesium chloride with potassium, and he then studied its properties. After that, Michael Faraday reduced dehydrated magnesium chloride by electrolysis and obtained pure metallic magnesium in 1833. For magnesium production industry, until 1868, Germany was the only magnesium producer in the world, using magnesium mostly as powder or ribbon for flashlights and other pyrotechnic purposes, and as a reducing agent in the production of aluminum. Here is a YouTube video demonstrating burning magnesium. Let's have a watch, but there is no sound. I hope it can work. This reminds me of the magnesium burning experiments done by my chemistry teacher like 20 years ago. My classmates and me were all impressed by the sharp bright light, which you can see in the fireworks shows. For example, we have a fireworks show every year in Sheffield. Without magnesium powder or particles, we cannot see the white sparks of a firework. Certainly, magnesium is not only used for entertaining people like fireworks. Historically, magnesium was one of the main aerospace construction metals and was used for German military aircraft as early as World War One and extensively for German aircraft in World War Two. The Northrop XP-56 Black Bullet was a unique prototype fighter interceptor. First airplane nearly completely designed with magnesium, built by the Northrop Corporation. It was one of the most radical of the experimental aircraft built during World War II. However, it was unsuccessful and did not enter production. B-36 bomber contained 19,000 pounds of magnesium. The service experience in B-36 in all environments proved magnesium's ability to withstand all requirements as satisfactory aircraft structure material. After World Wars, magnesium alloys are in use around the world in a variety of different applications. It is a preferred material when looking for weight reduction without compromising overall strength. The most common applications are in automotive industry, housings, transmission cases, engine blocks, steering wheels, and columns, sales frames. Recent change to the aircraft sales design standard now permits the use of magnesium alloys, meeting specific FAA flammability criteria. In passenger aircraft sales frames, and investigations are underway to allow broader use within the cabin. Magnesium is also become popular to be used in cases of laptops, televisions, cell phones. In addition, magnesium is also much more comparable to natural bone than other materials in regards to fracture toughness, elastic modularness, and compressive yield strength. Uncoated magnesium implants can be biodegradable in body fluids through corrosion, which eliminates the need for a second surgery to remove implants. At the same time, magnesium is still used in military applications. The magnesium alloy's applications are strongly associated with its own physical properties. Magnesium is a shiny silver or gray colored metal that is light in weight and strong. It is the lightest structural material with a density of 1.74 grams per cubic centimeter at room temperature. But it has a hexagonal close-packed crystal structure. Its C/A ratio is 1.624, which is bigger than HCP alpha titanium. The C/A ratio of titanium is 1.587. This little difference between magnesium and titanium results in different deformation behavior in these two alloy systems. Pure magnesium has an ultimate tensile strength in the range of 80 to 180 MPa and limited ductility, which is highly dependent on processing history. The melting point of 650 Celsius degrees is quite similar to aluminium, but the boiling point of 1090 Celsius degrees is less than the half of aluminium boiling point. This limits the magnesium applications. For example, magnesium alloys are difficult to 3D printing due to the high chemical reactivity that pose a combustion risk, and the low vaporization temperature of magnesium further increases the loss of magnesium and contaminates the additive manufacturing equipment's chamber. This table also lists other properties of heat capacity, fusion heat, normal potential, etc., which need to be considered for specific applications. Magnesium has an atomic number 12 with atomic weight 24, one of the alkaline earth metals of group 2 of the periodic table. The magnesium electron configuration is 1s2, 2s2, 2p6, and 3s2. Compared to other alloys, magnesium has the following advantages. It has lowest density of all construction metals at 1.74 grams per cubic centimeters. High special strength, which is the ratio of strength over density. It also has excellent casting ability, and steel molds are normally used. It has very good machining ability. Sometimes the lubricant oil is not necessary. Due to porous magnesium oxide film, corrosion resistance is not good, but the corrosion resistance can be largely improved with high purity alloys. Magnesium has high damping properties, and damping capacity is the ability of a metal to absorb energy. It can be also well welded under inert gases. Last but not least, magnesium can be fully recycled while paper routes. On the contrary, magnesium alloys have several disadvantages, which strongly hinder magnesium alloy applications in several industry sectors. The biggest scientific issues are poor cold work abilities, and room a lower temperature because of its HCP structure, and poor corrosion resistance, which causes safety risk when the component is in service in hot or humid environments. Magnesium is highly flammable when the temperature is around melting point, and the magnesium burning produces a large amount of heat. During solidifying and cooling, shrinkage can be easily introduced. Finally, it has low toughness and strength, which make magnesium alloys are not competitive to aluminum alloys. There are three main methods for magnesium extraction. For calcination, magnesium carbonate is heated to produce magnesium oxide and mixed with petroleum coke and then heated to separate oxygen from magnesium. Pidgeon process is one of several reduction methods. The ferrosilicon and magnesium powder are heated under vacuum at temperature around 1200 Celsius degrees, leaving magnesium vapor, which is then condensed. The commonly used electrolysis process is Dole process. Dolomite, calcium magnesium carbonate, and seawater are treated with hydrochloric acid to give magnesium chloride and put in electrolytic cell to give magnesium metal at cathode. The left part shows the flowchart and image of Pidgeon process. This process uses horizontal steel tubes called retorts in furnaces and under vacuum. In the retorts, mixtures of finely ground calcined dolomite and ferrosilicon form into briquettes, react to form magnesium vapors, which are condensed and later remelted into ingots. The Pidgeon process has long been considered uneconomic and outdated. The Chinese use this process to produce magnesium with superior raw material, good location, a large supply of skilled labor, and no capital costs. The selling price of magnesium in China is the lowest in the world, while the pound-for-pound price is even lower than that of aluminium. The right part of this slide shows magnesium production based on the Dow process and the Mag plant using Dow process to produce magnesium in Grace Salt Lake, Utah. A magnesium chloride solution is produced by adding hydrochloric acid to magnesium hydroxide extracted from the seawater precipitate. The solution is then condensed by heating and dehydrated in order to minimize the formation of magnesium oxide due to the decomposition of magnesium chloride. Dehydration is terminated at the stage that one molecule of crystal water remains. The byproduct chlorine from the electrolytic cells is recycled into hydrochloric acid for use at the front end of the process. As mentioned before, magnesium has an almost HCP crystal structure. However, this close-packed structure restricts the ability of deformation at low temperatures. For example, less than 225 Celsius degrees. And the primary slip occurs along the close-packed direction 11/20 on the close-packed plane 0001. As one Mrs. stated, at least 5 independent slip systems are required to plastically deform uniformly without failure. However, the strain on basal plane produced by the third can be produced by a simple adding of the previous two. So only 2 independent slip systems are available. Because of inadequate slip systems at room temperature, deformation causes fracture or twinning. Thus, other non-basal slip systems or mechanical twinning need to be activated to facilitate plastic deformation. As shown in the schematic figures, the prismatic 1/100 and first order paramedic 10/11 planes share the same close-packed direction 11/20 with the basal plane. Slip can also be activated on these two planes. Only 2 more independent slip systems can be added on the prismatic 1/100 and the primary paramedic 10/11 planes along 11/20 direction. Some researchers reported that a feather C+A slip system slip on the second order paramedic 11/22 in the direction of 1/123 can be triggered in HCP metals to provide the remaining slip system for full plasticity. It is named C+A slip because a Berger's vector of dislocation is composed of both the C and A directions. Due to limited activity slip systems at room temperature, deformation twinning readily prefers to be the candidate to enhance the deformation ability at room temperature. When material is subject to external shear force, it can produce twinning. Some plastic strain is usually accommodated by the rapid formation of mechanical twins, and an increase of the uniform elongation takes place. Often, mechanical twinning occurs on pyramidal planes 10 by 12, and sometimes it can be observed on 10 by 11 and 10 by 13 planes. 10 by 12 twinning allows string under z-axis tension. In addition, compression twinning 10 by 11 is activated for compression along the z-axis, which can reorientate the basal plane for slip. The double twins consist of the primary planes with the secondary planes, including 10 by 11 to 10 by 12 and 10 by 13 to 10 by 12 double twins. However, twinning only gives shear strain in one direction instead of the three from dislocation slip, so it cannot be treated as an independent mechanism of deformation. Once the temperature is higher than 200 Celsius degrees, it should be noted that the temperature varies with different alloy composition. Non-basal slip systems, including prismatic and first-order pyramidal slip systems, are activated and substitute for mechanical twinning. It is now very easy to use optic microscope, SEM, EBSD, and TM to observe and index deformation twinning types in deformed magnesium samples. For example, in this EBSD image, TTW is short for tension twin, CTW is short for compression twin, and DTW is short for double twin. The different twin types were color-coded according to their unique disorientation angle axis in this EBSD special grain boundary map. For example, TTW is color-coded in red and has a misorientation angle axis of 86 degrees along 1/10 direction. These sets of high-angle annular dark-field stamp images also display three different twin boundaries, including 10 by 11, 10 by 12, 10 by 13 twinning in nanoscale. The white dot in the images are the segregated anion atoms distributed along twinning boundaries. Dislocation glide in magnesium alloys occurs when the critical resolved shear stress CRSS in a special slip systems causes a gradual reorientation of atomic planes. There are three common slip modes in magnesium alloy systems. They are basal A, prismatic A, and pyramidal C plus A slip. A direction is what we said 11/20 direction, and C direction is 0001 direction. Each of these modes has different CRSS for slip movement. Deformation of magnesium alloys primarily occurs by basal A slip in the most densely packed basal planes 0001 and in the 11/20 direction. This is because of the low CRSS required to activate slip movements in the basal plane. For instance, basal slip CRSS is approximately 1% of non-basal slip at room temperature. Beyond slip in the basal plane, a dislocation movement also occurs in prismatic plane at CRSS values lower than CRSS for pyramidal slip. Slip in the pyramidal plane takes place by the movement of both A and C+A type dislocations. And this snip mode have enough independent snip systems to accommodate plastic strains within a material. As shown in this figure, these prismatic and pyramidal snip modes can only be easily activated and at elevated temperature and high CRSS values. If non-basic snip systems are not favorably activated, the tension twin or compression twin will be produced in grains with suitable orientations. The difference in CRSS values required to activate snip twinning in the different deformation modes partly results in anisotropy in magnesium alloys, because the orientation of crystals vary locally in the material. Magnesium is readily available commercially with purities exceeding 99.8%, but it is rarely used for engineering applications without being alloyed with other metals. Because the strength of the pure magnesium is too low, the property profiles demanded by automobile and other large-scale potential users of magnesium have revealed the need for alloy development. This figure shows the different trends in alloy development depending on the main requirement. For example, high special strength, good ductility, creep resistance, fiber and particle reinforced magnesium composite. A binary magnesium aluminum alloy provides the optimum combination of strength and ductility. The figure shows the further development of magnesium aluminum for die-casting magnesium, aluminum manganese, and for root alloys, magnesium aluminum zinc, and for sand casting alloys with manganese silicon, magnesium aluminum casting, and rare earth element. The development of magnesium lithium and other X-factor elements is a development of superlight alloys. Addition of lithium decreases strength but increases ductility. There is a need for a series of alloys with very high ductility capable of being formed by thermomechanical treatment. Ductility is determined by the number of operative snip systems. Since limited snip systems are activated at lower temperature, the ductility is normally not good in magnesium alloys. Expensive alloy elements like silver, rare earth elements, and scandium were added to the alloys and proved that these alloys are successful examples of high creep resistance magnesium alloys. However, the high cost restricted their applications. Compared with the magnesium alloys, magnesium matrix composites have many advantages, such as high elastic modulus, high strength, excellent creep resistance, and wear resistance at high temperature. However, their ductility is reduced, which limits their wide application. In next lecture, we're going to go through various magnesium alloy systems in details. Thank you for today. See you soon.